Alright, hey guys. By now you guys should have looked at the drill, completed it, and checked your answers up on the board. Hopefully that went okay for you guys. If you do have any questions about the drill, it's something I can cover when I come back, or you can come see me at Nest. Alright, so we are going to um, get full into our trig unit at this point. Okay, so the objectives for today. You guys need to watch this video and take the best notes that you can. If there is any issue with taking the notes and maybe you just can't keep up with the notes and things are moving too quickly as I'm going through them, this will be posted on YouTube and the link will be on Edmodo at some point in time on Monday. So you can go back and rewatch it if you need to get the notes and do a little bit better. Alright, that being said, let's get started. So the objective, we are going to determine arc length given a central angle and radius by converting into radians. So we're going to start off with some basics. A central angle is formed between what's called the initial and the terminal side, which is created at the origin. The origin for most of these circles is going to be right in the center. Right there. No, not really. Try again. About right there. Alright, this central angle that we're going to have is actually called theta. T-H-E-T-A. And it is represented by this particular symbol, and again, this is a Greek letter. It's basically a circle with a line right through the middle. That's theta. And the symbol works just like a variable would, so it's like x, but it's for an angle, so we call it theta. Alright, so the idea is we're going to have a central angle. So that means we're going to start here at the origin, go out to some point on the circle, and then we're going to create an angle someplace else on the circle, and the angle that's in between here is what we call theta. The distance from here up to here around the outside of the circle is the arc of the circle. And for whatever reason, they denote this with an S. Still have yet to figure that part out. So the distance from here to here around the outside of that circle is the arc. And that's denoted with an S. In order to actually find the arc, it's actually a pretty simple formula. The arc is the length of the curve around the circle between an initial and a terminal side. And we've talked about initial and terminal sides and stuff like that already. So the formula for the arc length is S equals R times theta. Okay, again, relatively easy formula to know. The arc length is S, R is the radius, which will have units. The arc length will also have units. It'll be the same units, whatever they are, feet, centimeters, etc. And then the central angle, and the important part about this is that it must be in radians. You cannot have a central angle that is measured in degrees in this case. If it is, you have to change it to radians before we can do anything with it. Alright, so arc length, again, this is relatively simple stuff. Let's try an example. Determine the arc length of a sector with a diameter of 24 centimeters and a central angle of pi halves radians. So we need to write down the formula. It might be a good idea until you get used to it just to write the formula. S equals R theta. Determine the arc length. We are looking for S. We don't know it. But what we need is the radius and the central angle theta. Well, they gave us the angle of pi halves. What they didn't give us was the radius, but they gave us the diameter. Of course, the diameter is twice the radius, so the radius is going to be 1/2 of the diameter. So our radius is 12 centimeters. And they told us that theta, our central angle, is pi halves radians. Again, with the exception of probably the last two problems on here, this is all non-calculator stuff. If you have your calculators out, put them away. You need to start practicing now. So the arc that this thing creates around the outside of the circle is 12 times pi halves. And again, remember, if you multiply a whole number or a non-fractional number like 12 times a fraction, it only gets multiplied on the top. So this becomes 12 pi over 2. Again, treat pi kind of like a variable. It's not, but treat it like one. So that becomes 6 pi, and this does have units because it's the length of an arc, 6 pi centimeters. Okay, pretty easy stuff. Sometimes, however, we're not looking for the arc. Sometimes they'll give us the arc and we're looking for either the radius or the central angle, like in number 2. It says determine the central angle measure of a sector with a diameter of 12 feet and an arc length of 3 pi fourths feet, expressed as a fraction in simplest form. So we are trying to determine the central angle, which means we are looking for theta. That's what we don't know. So they've given us, again, they gave us diameter, not really sure why, but that tells us that the radius is 12 feet. I'm sorry, the radius is 6 feet, half the diameter. And they told us the arc length is 3 pi fourths feet. All right, plug these things into your formula. So the arc length is 3 pi fourths, and that's going to equal the radius times theta, which is our central angle. In order to solve for theta, we need to divide both sides by 6. Dividing a fraction by something is like multiplying by the reciprocal. So hopefully you guys remember that dividing this thing by 6 is the same thing as multiplying by the reciprocal of 6, which is 1/6. And we want to go ahead and put this thing in simplest form. This is going to give us 3 pi over 24, but 3 goes into both of those. So we're going to simplify that to pi over 8, or pi eighths radians. You do not actually need to put RAD at the end for radians. It is understood to be radians. So that's the one time you actually don't need to include a unit. All right, you guys go ahead and give these a shot. I am going to go ahead and work them out for you guys, but I'm just going to write it up there. So as I'm writing, you guys should be trying to work this out at the same time. All right, hopefully you've had enough time to work these out on your own. If you haven't, the answers are up there. Take a look real quick. I'll leave this up for a few more seconds, and then we're going to move on to the next problem on the next page. Again, you should have been able to do all of this without the aid of a calculator, including the reducing the 180 over 270, and then the cross multiplication and dividing. Even if it takes you a few extra seconds. All right, we're going to move on. Again, if you didn't catch all this, it is going to be on YouTube, and the link will be on Edmodo. All right, we are going to walk through number 5 together. A wedge-shaped slice is cut from a circular pizza, so standard pizza. The radius of the pizza is 8 inches. Yay, they give us the radius this time. And the rounded edge of the crust of the slice measures 6.4 inches. So what have they given us? They gave us the radius is 8, and the rounded edge, that's kind of the outside of the pizza, so that's the arc length of this thing. So they're giving us that S is 6.4 inches. What's the angle of the pointed end of the pizza slice? So you're talking about the center of the pizza there. So we are talking about basically a circle. We're looking for the angle. We're looking for theta. We want to do this in radians to the nearest tenth. So S equals R theta. S is 6.4 equals the radius, which is 8, times theta. Now you might be thinking, wait a minute, there's decimals here. I don't know how to deal with that, but you do. I'm going to divide both sides by 8. At the very least, we should know that much. And then you might think, well, wait a minute, I don't know how to figure out 6.4 divided by 8, but you really do. If you ignore the decimal point, you should know how many times 8 goes into 64, or 64 divided by 8. Hopefully you know that 8 squared is 64, so 8 times 8 is 64. So 6.4 divided by 8 is really just going to be 8, but with one decimal place, 0.8. So your angle is 0.8 radians. And again, that would be something you should be able to do without the aid of a calculator. This will be expected. The last two are challenge problems. So while we're not going to actually cover everything from the challenge problem, I want to at least go over the concept here of what's going on. I'm not going to give the answers on these because they are challenge. I want you guys to try and figure them out. These kind of questions, you would be able to use a calculator. All right, so number 6 says the diameter of Earth is 7,917.5 miles. A U.S. space shuttle is flying at an altitude around 200 miles above the Earth. How far did the shuttle travel if the central angle from the Earth is 215 degrees? All right, so let's go back to the general idea here. First of all, we got the Earth. We'll make the Earth blue. It says the diameter of the Earth is 7,917.5 miles. So the diameter, of course, goes straight through the center of the Earth. But we don't ever use the diameter when it comes to arc length. We're only going to use the radius. So whatever the diameter is, we're going to know that the radius is 1/2 of the diameter. So that's this distance right here. That's R. But it says that the space shuttle is flying at an altitude of 200 miles above the Earth. So the space shuttle is someplace out here. It's 200 miles above the Earth. It's flying in orbit. And it says that the Earth is traveling in orbit. Let's see, it's flying around at 200 miles above the Earth, and it creates an angle of 215 degrees from the center. So this thing is moving around the Earth this way, but it's created this angle, 215 degree angle. So this black arc that I've created on the outside there, that's the arc length, that's the total distance that this space shuttle has traveled. when it's gone 215 degrees around the Earth from where it started. So it's still the same exact idea. You're going to know that this is 215 degrees, which means you're going to have to change it into radians. So you'll have to do that first. Once you have that, you'll have the central angle. You already have the radius because you're going to divide 7,917.5 by 2 and get the radius. Then you plug it in to get the arc length, which will give you the distance that this thing traveled around the Earth. So that's the general idea behind this challenge problem. And number 7 is relatively similar to that. So go ahead and try those two on your own. All right, at this time you need to take out the second packet, which looks like this. Okay, part 2. This one you may need to go back and watch again if you can't follow this one, because I am going to run through this stuff relatively fast, but hopefully if you've been doing the other videos that we've had and you've understood those, then that's going to really help you with this. So the idea is what we're going to be doing is building what is called the unit circle. And the reason it's called the unit circle is because the word unit in math tends to mean 1. So this is a unit circle where the radius is 1. It is simply a circle where the radius is 1. So what we're going to do is we're going to build some of the important pieces of the unit circle. We should already know a few of these things because we've already covered it. If you start on the positive x-axis and I don't go anywhere, in other words, I don't create an angle, we should already know that that is 0 degrees, which is the same as 0 radians. There's no movement around the arc if I don't have to move at all. We also should know that one full circle all the way around clockwise or counterclockwise, doesn't really matter, but counterclockwise is actually the typical way we go, is 360 degrees. So I'll start and I'll end at exactly the same spot. Start here, go all the way around. You don't have to draw that. I'm going to actually erase mine. Try to. There we go. And 360 degrees, we've already said, is 2 pi radians. Okay, well likewise, we should know half a circle is 180 degrees. And by virtue of the same concept, if we're going to do it in radians, half of 2 pi would simply be 1 pi, or just pi. Okay, same exact concept. If I am going to build, and again, you don't have to draw this part, if I am going to build that angle right there, well, you should pretty much know that if I'm going up to that specific angle, that is a 90-degree angle. So again, I'm going to erase that little box. But at the top here, that's 90 degrees. Because 90 is halfway in between 0 and 180. Same concept. If I'm going to build the middle of that in radians, halfway between 0 and 1 full pi would be half a pi, or the way we write it is pi halves, pi divided by 2. And then at the very bottom, if I'm counting by 90s all the way around, 0, 90, 180, the next one would logically be 270. And then same concept, if I started at 0 radians, I had a half a pi at the top, I have a whole pi at the left, that's 0 pi first, 1/2 of a pi, 2/2 of a pi, which is pi. The next one down here at the bottom would be 3/2 of a pi, or 3 pi over 2. And then 4/2 of a pi all the way back to the right side would be 4 over 2 is 2 pi. Okay, those we should already know. One of the other things we're going to need to know is we're going to need to know these values. There are points on the XY axis associated with all these different places on the unit circle. These shouldn't be too hard. These should actually make sense, because if you think about it, we said the radius of this, because it's a unit circle, is 1, which means if I go all the way out to this point right here in blue, well, I went 1 in the x direction, and I didn't move vertically at all, so 0 in the y direction. That is the point 1, 0. Okay, if I go all the way to the left instead, over here now, well, that just means I moved 1 unit in the left direction, so that's -1 in the x, and still didn't move vertically, so 0 for y. Same general concept up and down, but this time instead of x moving, because I'm not going to move left or right, it's going to be the y. So if I go up to pi halves, that point is 0 for x and 1 for y. And again, all this is because the radius, or the distance from the origin out to all of these points, is 1. And then all the way down, 0x, -1 for y. Okay, those 5, and I say 5 because 2 of them are coterminal, the 0 and the 360, or 0 and 2 pi, those are coterminal. They have the same point at that point, but they aren't different angles. Those 5 points, excuse me, are what are called quadrant angles, because they lie specifically on the x or the y axis. It's these other ones where you see the blue arrows, those are going to be the ones that are slightly more challenging. So what we're going to do is we're going to build those points. And once you know the arrows here in that first quadrant, everything else is actually going to be relatively easy. As long as you have some pattern recognition, you're going to be able to start seeing how all this stuff relates together. And eventually you're going to have to know all of these unit circle values, because you're going to get to fill one of these things out for quizzes on your own. So let's talk about what we've got here. The first one, from here to there, is supposed to be 30 degrees. And that's one of our special ones right there, 30 degrees. The next one is supposed to be 45 degrees. And then the last one, while it's not drawn very well, because it's way too far away, is supposed to be 60. All right, and each one of these angles, each one of those central angles that we have there, is associated with a point on the circle. 1 point here, 1 point here, 1 point there. Well, it's no coincidence that we have one of these associated with a 30, one with a 45, and one with a 60. This is why we did the videos on the 30, 60, 90, and 45, 45, 90 right triangles. So we're going to go to the next page, and we're going to show how all this stuff relates. So the first thing we're going to do is understand that, again, every one of those points on the circle is associated with an actual coordinate, an xy value. It's not as easy as -1, 0, 1, 0, stuff like that, because it's not going to be out one full unit from the x or the y axis only. So to find these points, we're going to use some of the knowledge of special right triangles that we had you guys work on the other day. So the first one we're going to deal with is the 45, 45, 90. So this angle right here is supposed to be a 45-degree angle. Well, it is associated with a point. The one good thing is I know that distance, because that is the radius from the center of the circle out to a point on the arc. I know that distance to be 1. It's a unit circle. Remember that a unit circle has a radius of 1. All right? Well, if we have a 45, 45, 90, and I know this is 45, 45, 90 because the one angle that I have drawn is 45, the right angle is just to the right of that, and then the top is also 45, which I'm not going to label. If it's a 45, 45, 90, you should remember that the relationship between a 45, 45, 90's legs and its hypotenuse is that if you know one of the legs, which are the pieces that we're missing, it's the leg times the square root of 2 will give you the hypotenuse. Well, if it's a leg times the square root of a 2 to get the hypotenuse, if I have the hypotenuse to get back to a leg, I would simply divide by the square root of 2. So the leg here is going to be 1 divided by the square root of 2. And because this is a 45, 45, 90, the other leg has to be exactly the same. So this vertical distance right here also must be 1 over the square root of 2. The horizontal one I found first there, then the vertical distance is 1 over the square root of 2 over 2, 1 over the square root of 2. Well, that means the x direction was 1 over the square root of 2. The y direction was 1 over the square root of 2. So my point on this chart is 1 over the square root of 2, 1 over the square root of 2. That's the actual point on the curve. Okay, now we're going to wrap this around to one of the other videos, which was rationalization, because while there's nothing wrong with leaving 1 over the square root of 2 as an actual point, it's not commonly seen that way. If you guys remember, if I started off with 1 over the square root of 2, and I wanted to do what was called rationalizing, rationalizing means you have to get the square root out of the denominator. And in order to do that, we needed to multiply this by the square root in the denominator, which is the square root of 2, over the square root of 2. And I have to do it on top and bottom because I have to be multiplying by a factor of 1, otherwise I'm changing the fraction. Well, so that's going to give us on top the square root of 2, and if you guys remember, square root of 2 times itself, square root of 2 times the square root of 2 is just going to give you what's underneath the radical, which is 2. So it's more common that you're actually going to see this point written as the square root of 2 over 2, square root of 2 over 2. But what's really important here is that you understand that 1 over the square root of 2 and the square root of 2 over 2 are exactly the same value. They mean the same thing. They're just written in different ways. All right, so that developed that point at the 45-degree angle. We're going to move on to the next page. And this one, you can see that we have two different triangles. The one on the bottom, what I'm going to highlight here in blue first, that one right there is a 30-degree angle. So your central angle is 30 degrees. Well, if I have 30 there and I have a right angle to the right, that means the other one has to be 60. So this is a 30, 60, 90 right triangle. And again, the one side that I definitely know is the hypotenuse. Hypotenuse is 1. So, being a 45, 45, 90 or a 30, 60, 90, the good thing is you only ever need to know one side, and you're going to be able to figure out the other ones as long as you remember the relationships. Well, I know the hypotenuse, that's 1. I know that the short side, or the side opposite of 30 degrees, is always going to be half of the hypotenuse. Because if you remember, the relationship was if you had the short side, to multiply that by 2 to get the hypotenuse. So since we have the hypotenuse, the short side is 1/2 of the hypotenuse, and then half of 1 is 1/2. That is that side right there. And then the other relationship was, if I know the short side, the long side, using Pythagorean theorem, will always be the short side times, oops, that's horrible, times the square root of 3. And again, it's going to be the square root of 3 times 1/2. The square root of 3 is not a fraction, so it just goes on top. So this is going to be the square root of 3 over 2. So my x direction, the x value was square root of 3 over 2. The y value in the y direction is 1/2. So that point, when you have a 30-degree angle from the center, makes square root of 3 over 2, comma, 1/2. And then our last triangle. You should remember that the last angle that we had to deal with, from here up to there, was a 60-degree angle. Well, again, it should kind of make sense. This is 60 degrees. This right here is a 90-degree angle, which means that the one up on the top is 30. So it really just means this is another 30, 60, 90 right triangle. Just that they're in different places now, that's all. So we need to figure out this value and then that value. Well, again, the one thing I know is that the hypotenuse is 1. That's the radius. So now the only difference is the short side is on the bottom. Should be the same values though, right? It's exactly the same type of triangle. The short side is 1/2 of the hypotenuse, so that's a half. The long side is always the short side times the square root of 3, which will be the square root of 3 over 2. The only thing that really changed was the x and y value. And as a matter of fact, hopefully what you can see is all they did was they flipped. Which actually makes knowing the 30 degree and the 60 degree values pretty easy as long as you keep them straight, as long as you don't get both of them backwards. If you know one, you know the other one. So you should see that the 30-degree angle creates the square root of 3 over 2, 1/2, where the 60-degree angle creates 1/2 square root of 3 over 2. If you know one, you know the other one because it's just going to flip the x and the y. All right, again, if you're having a hard time keeping up with all this stuff, go back and watch it later because now we're going to build the entire circle. And this whopping thing right here is what you guys are going to all have to be able to do. You're going to have to be able to fill out one of these entire circles. And these tests, when you get them, will be timed. They will be non-calculator. And you're going to have to be able to do them relatively quickly. So, again, pattern recognition is going to be key. You could try to memorize the whole thing, which I have seen people do, and that's up to you. But if you can figure out the patterns that I'm going to go through, it's going to make it a lot easier. All right, so one thing you definitely need to know, you need to know your quadrant angles, which again are on the XY axis. So 0 degrees went with 0 radians, 360 went with 2 pi. 90 degrees was pi over 2. 180 degrees was pi, and then down at the bottom, 270 was 3 pi halves. So again, think of it in terms of splitting a pie into halves and just counting the number of halves as you go around. Biggest thing is you must reduce everything as you go. The points associated with those, we've already gone through it. The point associated with 0 was 1, 0. 1 in the x direction, 0 in the y direction. The point associated with 180 on the left was -1, 0. 1 to the left, nothing in the y direction. At 90 degrees, it was 0x, 1y. And at the bottom, it is 0x, -1y. Okay, that we've already dealt with in the past, but you need to know those or be able to figure them out very easily. All right, we have dealt with the first quadrant. And what I'm going to tell you is if you know the first quadrant, you should be able to figure everything else out. So the first quadrant we've already dealt with, 30 degrees. Let's figure out how to transform that into radians without using a formula. Let's see if this makes sense. If I were to split this up, and I'm going to draw this, you probably shouldn't draw this on yours. If we were to split this up, 30 degrees is there, 60 degrees is there, but all that really is another 30 degrees if you think about it. So I've got a 30 degrees, 60 degrees. The next one takes you up to 90 degrees. The next one takes you up to whatever that's going to be. And then out here, if you really think about it, 30 degrees goes into 180 degrees exactly how many times? 6. 1, 2, 3, 4, 5, 6 to get over to 180? Well, if you're going to split pi up the same way, you're dividing pi by the same number of wedges that you had to get over there. So 30 degrees is really pi divided by 6 wedges, or pi sixth. If you use the same logic, I'm going to erase. If you use the same logic here, if I divide into 60, 60 goes into 180 3 times. So if I'm going to take pi and divide it into the same increments, I'm dividing pi into 3 equal wedges, which is pi over 3. And then one more, same logic. If I were to take and divide this by 45 degrees, 45 goes into 180 4 times, because it would be 45, 90, 135, 180. 45 goes into 180 4 times, so if I divide pi by 4, it will be pi fourths. Okay, so we hadn't talked about how to convert those yet, but you're going to need to know those values specifically very quickly. So again, just think about 30 degrees goes into 180 6 times, therefore pi would have to be divided by 6. 45 goes in 4 times, so pi would have to be divided by 4. 60 goes in 3 times, so pi would have to be divided by 3 in order to get those particular radians. This is going to save you a lot of time from having to try and do a formula for every single one of these, because again, these quizzes will be timed. We've already talked about the values for 30, 60, and 90. So the point associated right here with 30 degrees was square root of 3 over 2, 1/2. The point associated with 45 degrees, or pi fourths, was square root of 2 over 2, square root of 2 over 2. That one's nice because they're exactly the same. Makes it real easy. And if you know 30, you know 60, because it's just going to flip the values. 1/2 square root of 3 over 2. So the trick is, how do I figure out the rest of this stuff? The degrees should be the easy part. Again, ignore the ones in the middle right now. So we're going to ignore this one. Don't put X's on your paper, because I'm coming back to it and erasing it. We're going to ignore the ones in the middle I just X'd out. Every other one of those is counting by 30 degrees. So as long as you can keep adding 30 repetitively, you should be able to figure out all those degrees. So if you think about it, we had 30, 60, 90. The next one adding 30 should be 120. Then 30 more would be 150. 30 more is down here at 180. Adding 30 more, 210. 30 more, 240. Adding 30 more, we've already done 270. It's down at the bottom. 30 more is 300. 30 more onto that, 330. And then all the way back around to 360. So we're good. So that's pretty easy to do, just adding 30 around there. The ones in the middle, we know that we're adding 45s. So you have to be able to add 45. So the one we started off with is 45 degrees. Add 45 more, we're at 90. So you got to add 45 to 90, which is 135. Adding 45 to that gets you down here to 180. Adding 45 to 180 is 225. 45 to that is 270, and then 45 to that one is, I'm going to have to take off my red X over here. So 45 onto 270 is 315. All right, so we've worked all the degrees out. Again, the degrees are not terribly difficult to do. You just have to know what you're adding to get to each piece. Putting them in radians. Again, this is where I said if you know the first quadrant, you can figure the rest of this stuff out. To put this stuff into radians, let's think about this. 30 degrees is 1/6 of a pi. 60 degrees is technically 2/6 of a pi, but if you think about it, 2/6 reduces to 1/3, which is why we have pi thirds. 90 degrees is 3/6 of a pi, but 3/6 reduces to 1/2, or pi halves. So the next one, right over here at 120 degrees, is going to be 4/6 of a pi. But that reduces, so we can't write it like that. Sorry if you're going to have to erase there. 4/6 reduces. It must be in reduced form. 4/6 reduces to 2/3. So this is 2 pi thirds. The next one, because that was 4/6 pi, is going to be 5 pi over 6. That does not reduce, so we're going to go ahead and leave it like it is. The next one would be 6 pi over 6, but 6 pi over 6 is just pi, so that's the 180. The next one would be 7 pi over 6. That does not reduce. The next one would be 8 pi over 6, but 8 pi over 6, 8/6 reduces to 4/3, so it's 4 pi thirds. The next one would be 9 pi over 3, but that reduces to 3/2. That's at the very bottom. The next one would be 10 pi over 10 pi over 6, not 9 pi over 3. It would be 9 pi over 6 at the bottom, and then 10 pi over 6 at 300. 10 pi over 6 reduces to 5 pi thirds. And then the last one, which would be 11 pi over 6, does not reduce. So we've got all of our sixths. Again, if you can start to see the patterns, wonderful. If not, we'll work on it. Okay, now all we have to do is fill in everything that ends in a 5. 45, 135, 225, 315, all of them end in 5. Good news is they all have 4 in the denominator. The first one is 1 pi over 4. 2 pi over 4 is at the top where 90 degrees is, but 2/4 again reduces to 1/2. So the next one logically would be 3 pi over 4. At 180, that would be 4 pi over 4, which reduces to pi. So the next one is going to be 5 pi over 4. And then the last one, because we would go to 6 pi over 4, which reduces to 3/2, would be 7 pi over 4. So what you should notice is that everything that ends in 5, all of your angles that end in 5 for degrees, are something over 4. And if you look at it, I've got 1 pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 for my 4 quadrants. It's all the odd powers, odd numbers of pi over 4. If you can see this, I'll do this in red. This and this are symmetric. It's also symmetric to this, and I'm trying to do this in my own way, in my own shadow here. That. Those are symmetric. They create what's called a bow tie pattern. They are exactly 30 degrees away in this direction, in this direction, in that direction, and in that direction from the x-axis. If that's the case, they create the same point. And what you should notice is that every single one of them has a 6 in the denominator. All the ones that are 30 degrees away from the x-axis have a 6 in the denominator. The good news is, because they are exactly at the same place on the circle, just on opposite sides, every point is exactly the same, which means This is the square root of 3 over 2, 1/2. This is the square root of 3 over 2, 1/2. This is the square root of 3 over 2, 1/2. The only difference is the signs. Remember, we talked about which quadrant things were in would determine what sign things are. The signs here are going to be different. So some of these will be positive, some of these will be negative. Well, anything in quadrant 2, x is negative, y is positive. In quadrant 3, they're both negative, and in quadrant 4, x is positive, y is negative. This same thing is going to hold true for all the rest of these points. Because of the fact that they are symmetric to the x and y axis, they are all going to be the same value. So you just have to find the symmetry. Anything that has a denominator of fourths will always be square root of 2 over 2. Square root of 2 over 2. Square root of 2 over 2, all the way around. Everything that has a pi fourths in it. And again, it's just knowing the signs. X is negative in the fourth. Both are negative in the third. I'm sorry, y was negative in the fourth. Both are negative in the third, and x is negative in the second. And then the last one is going to follow the same pattern. 1/2 square root of 3 over 2. 1/2 square root of 3 over 2. 1/2 square root of 3 over 2. And we got to plug in the negative in the second quadrant for x. Both of them are negative in the third quadrant, and then only the y is negative in the fourth quadrant. And that 1 down there at the bottom is just bothering me, so I'm going to erase that. Looked too much like a pi to me. All right, there you have it. There is the entire unit circle. Again, you're going to need to figure out what patterns that you're going to need to know, but if you can figure out, and this was the way I did it when I was in school, if you know the 4 quadrant angles, which means everything on the x and y axis, and I chose to know that one and that one. The reason I didn't memorize pi thirds was because if I knew pi sixth, remember it's just the opposite, you're going to flip the x's and the y's. So if I chose to memorize those two, I could figure everything else out. And when you really get good, you'll be able to complete one of these whole circles without being given any information within about 2 or 3 minutes, accurately. All right, a lot of information. The homework for you guys is the last page of this. We are going to deal much more with this unit circle stuff next class, so don't stress too much if you didn't figure it all out today, but please go back and watch it again if you need to, or at least go back to certain parts if you think you've missed some stuff. Next class, you are going to have a quiz, which is just going to be on changing degrees to radians and radians to degrees with no calculator, not these special ones right here, not the ones we just did on the unit circle, but just doing it in general, and the arc length formula, the S equals R theta. It's going to be a 6-question quiz. It will be timed. You're going to have to make sure you know how to do it. Again, will be without calculator. There will be one calculator problem because decimals get kind of messy on that one. Other than that, enjoy the rest of your day, and I will see you guys next class.